All right, so this is 2.4 worksheet 1. This is our first experience with DGES and solving problems with constant acceleration. So in this first problem, it says a person runs with an initial speed of 3 meters per second and accelerates at 0.2 meters per second squared. How long will it take them to reach a speed of 8 meters per second? So you'll see that we already had a diagram for this problem. It's got a person going slower and then faster. And then we have to consider what those givens are that I circled in the problem. So 3 meters per second is the initial velocity. 8 meters per second is the final velocity. And then acceleration is that 0.2 value. We're trying to solve for the time, and the equation is already chosen for us. So what we can do is we can substitute these values into the equation, and notice that we do substitute the positive or negativity of these values, because that's going to make sure that our result matches the directions that we started with for these givens. So then our solution, we start with the same exact substituted equation. I subtracted 3 from both sides to get 5 on the left, and then just 0.2t on the right. Divide both sides by 0.2 in order to get that the time would be 25 seconds. For the second problem, we have that a skateboarder initially travels at this speed and then slows down at a rate of that. How far will they travel in 8 seconds? And so once again, I circled the givens, and then I actually underlined the question for the unknown so that we can, because this time we have to actually determine what unknown this question is asking for. I drew a diagram of this skateboarder, so you see that they're moving at 7.5 at the left. Then they are slowing down, and we're trying to find out how far do they go while they're slowing down. The givens are an initial velocity of this, an acceleration of that. And notice that those two values have opposite signs, that my initial velocity is positive and my acceleration is negative, because they need to be opposite, seeing as this question includes something that's slowing down. So one has to be positive, one has to be negative for this to work. The time is 8 seconds, and then we gave you that the initial position is 0, because we're just going to figure out how far from that initial position of 0 did they get, and that's how far they went. We're trying to figure out what that final position is. And so if we substitute all values into the equation, we can then solve and get a value of 40.8 meters. And so this doesn't say that the skateboarder was going to the right. So really we just know that the distance that they traveled was 40.8 meters while they slowed down for 8 seconds. For number 3, we have a kite. Here I'm going to draw the diagram. It's moving to the left on the at the beginning of the diagram, but then the wind pushes it to the right, and so eventually it goes backwards, and it ends up 80 meters right of where it started. So we're trying to figure out what is the final velocity. Here are the variables that correspond with the given values in the problem. And we're solving for the final velocity. I just noticed that I made a mistake here, that it ends 20 meters right, and I put my diagram 80 meters right. So we'll see if that also follows through in my substitution. It doesn't. I substituted correctly, so that's great. And then the work shows all of that combined together. What we end up with is this equation, which is VF squared. First of all, let's talk about why we chose that equation. We chose that equation because we didn't have any mention of time in this problem, and the top two equations both need time, and so we couldn't use those. We had to use the bottom equation. And so one thing that can cause mistakes when using this equation is that the values are squared. And so when we're solving for a final velocity here, we end up with a number is equal to the final velocity squared. And so what we need to do is take the square root of that number And then what we get is two different solutions, a negative one and a positive one. And so this is where the diagram is useful, that at the end, after it's moved 20 meters to the right, at that point it will be moving right. It won't be moving left anymore. And so we know that the positive final velocity is correct and the negative one is not a correct answer. Both of them are potential correct answers, though, when using a square root. For number 4, we've got a soccer ball that's initially kicked at 6.2 meters per second to the left. It's rolling on the grass, it slows down, and then it stops 4 seconds later. And we're asking what's the average acceleration. So here is my drawing of the ball. It starts on the right side where it's moving to the left, and then at the left side it's stopped. And then for the givens, we have this initial velocity of negative 6.2 meters per second, and then this one might be somewhat complicated. The final velocity is 0, and that's because of the word stop. And the time it takes is 4 seconds. We're solving for the acceleration, and so as we look at the equations, this middle equation has all of the givens and unknowns that we are dealing with in this problem. We can substitute those values into this equation and then solve for A. First by adding 6.2 to both sides and then dividing both sides by 4 to get a positive 1.55 meters per second squared. Now notice that the answer is positive even though the ball is slowing down, and that's because the ball had an initial velocity that was in the negative direction. And so because the velocity and the acceleration had opposite directions, then the ball slowed down. For number 5, we have a cyclist that's starting at rest and moving to the right. So we've got a cyclist that starts at rest and accelerates at a rate of 0.75 meters per second squared for 15 seconds. I'm also going to circle at rest because that tells us what the initial velocity is, which is 0. We have a rate of acceleration, and then again we're just going to call the position that they start at 0 meters, because then we'll be able to solve for how far they get away from that. Our unknown is how far away or what the final position is. We'll pick the top equation because it has all the givens and unknowns that we're using. This is what it looks like if we substitute those values in. And you'll notice that this term and this term actually cancel out because of the initial velocity of 0 and the initial position of 0. And so what we end up with when we're trying to find a solution is a little bit more simple, and we get a final position of 84.375 meters. For the last question, it says a fully grown lion falls for 8 seconds before reaching the ground. How tall was the cliff from which it fell? And so we have a couple of things circled here. 8 seconds is time. The ground, we're going to say, is a specific position. And then falls actually tells us what kind of acceleration the lion is feeling. So here's my drawing of the lion. We know that because it's falling, it's free falling, the acceleration is g, or negative 9.8 meters per second squared. The time that it fell for is 8 seconds. And then we're going to call the final position that the line got to, the ground, 0 meters, because then that's going to tell us, that's going to allow us to solve for a higher, more positive number, which is where the line started, the top of the cliff. The initial velocity is 0 meters per second, and that's because that's how fast the line was moving right before Scar betrayed him, and then he fell to his untimely death. And the unknown we're trying to figure out is how high up did they start, or what was the initial position of the lion. So we have enough information to use the same equation as last time. We're going to substitute the values in for this and then solve for the initial position. And what we get in the end is that the cliff was 313.6 meters high.